Hello there. I welcome you back to today's class. In today's class, I'm going to talk about projected coordinate system. In our previous class, we spoke about geographic coordinate system. We've come to understand how datums are developed, and we've come to understand the naming convention of uh, coordinate system. However, there is another type of coordinate system called projected coordinate system. And one of the questions that I'm sure someone might ask itself is if WGS 1984 is a geographic coordinate system, like we said in our previous class, then everything is fine. Why do we need a projected coordinate system? In this class, I'll explain to you why we need projected coordinate system and then how projected coordinate systems are actually designed. We'll talk about GIS, Coordinate System Authority, and then we would look at some few examples. We'll try to combine everything together. So with the globe, the Earth as we see as a globe, we know it's spherical or it's curved on its surface. Maps basically has to be flat. And so if you look at this point, we are looking at maps and it's more like on a sheet of paper. If you are watching me, if I was projecting any map, you would be watching the map on a flat screen. Whether it's your laptop or you are watching it through a projector, it would be on a flat screen. Now, if we were to take the Earth and to spread it on a flat screen, this is how it's going to be like. We would have to cut some part out to be able to try to push it to be straight. However, in our attempt to do that, we are going to shrink certain places and expand certain places. So we are going to distort the true distances and the true shapes of objects on the globe if we are to do that. Thankfully, we don't have to do that, but we want to be able to keep the Earth spherical and be able to create a flat map that represents the curved part of the Earth. So basically, we would have to apply some sort of mathematical model to convert the coordinates on the curved surface to a plane. Now, I've already explained to you one of the reasons why we need projected coordinate system. That is, we need the maps to be on a flat surface. Secondly, we don't just use maps by looking at them. We have a couple of use that we do with map. One of them is we want to get directions. So we are interested in using the map to direct us from one point to another. We are interested to be able to get the true shape of objects on the surface of the Earth. We are interested in calculating the distances between objects on the surface of the Earth. And also we are interested in getting the measurements, like the areas of things on the surface of the Earth. Remember that geographic coordinate system we discussed and showed that geographic coordinate system is used basically in the form of angles. Its measurement is in the form of angle because in the geographic coordinate system we look at the position of objects in relation to the center of the Earth or the center of the globe. And so if we had degrees, imagine measuring this distance and finding out whatever value we get, and the value is in degrees. What does it mean to walk 1 degree or to walk 2 degrees? These are complicated. These operations are quite complicated to do. If some of them are not even possible at all, but it's complicated to do with geographic coordinate system or with degrees. And so we need to be able to convert the data or to convert the coordinates on the curved surface onto a planar surface. And how do we do that? So we apply mathematical formulas to be able to convert the degrees of the latitude and the longitude we have in the geographic coordinate system into a planar surface. Now, with this mathematical formula that we apply, we end up with three basic groups of projections. And I'm going to discuss them one after the other so we can get some understanding. But we are getting cylindrical, conical, and azimuthal projections. These are the three broad groups of projections that we have. Taking cylindrical projection, imagine that we can put a bulb inside the globe and we can see everything on the surface of the earth. If we are to fit this ball or this globe inside a cylinder, there will be two sides. There will be some part of the globe that would be touching the cylinder, and there will be part of it that will not be touching the cylinder. Now, if you look at the globe from top here, the distance or the gap between this globe and the cylinder top with the light radiation coming is going to make whatever that is here look bigger than it actually is. And the same thing will happen to when you are looking at the globe from this side or this side, or from this side or this side. However, when you look at the globe from where it is touching the cylinder, we are going to get exactly how things look like. And so this is a cylindrical projection. We assume that this is how it works, or we assume the bulb and then the cylinder. But in real world, you know that we are using mathematical formulas or algorithms. We don't necessarily take the earth and put it in the cylinder per se. Now, because of the touching of the globe to the cylinder at this uh, longitude or on this part of the equator which touches, which seems, I mean, generally we say that it's touching the cylinder, we get to preserve the direction and the shape. And so all the people or all the countries that will be found here, whatever measurement we measure here is actually the true directions or the true distances. And we can be able to measure shape, we can be able to measure directions exactly only on the places that touches the globe. However, if we turn the cylinder on the side and we try to move the cylinder, we try to move the globe such that it touches the areas along the longitude, we call this traverse. And so you may have seen coordinate system that has the name traverse in them, which we will come to it. And then if we are to tilt the cylinder and look at it from the tilted angle, we are going to have an oblique. So basically under cylindrical projections, we have the traverse projection, the oblique projection, and then we have the normal projection. And like I said, in cylindrical projection, we are preserving directions and shape. We come to conical projection. Same concept, but this time around we are not using cylinder, but we are using cone. So if you fit a cone on top of a globe and with a light inside the globe and looking at the globe from outside the cone, the parts, there are two ends that is likely to touch the globe. And when these ends touch, we are able to get the true shape, we are able to get the true size of things that are on the globe. And with that, we are able to preserve the area and distances. So with conical projections, or with conical projections, we are able to get the area and distances. These things are very important because when you are choosing your coordinate system for analysis, you need to think ahead of time. What are your priorities? If distances and areas are your priority, that is what you're finally going to calculate with the data, then you need to know that there are certain coordinate systems, there are certain projections that actually helps preserve these areas to the right ones, or to the what it actually is in the real world. There's something called secant projection under conical projection, which is basically when the cone is a slide, not just put on top of the globe, but a slide through the globe such that it can pass through the globe, and then it can touch the globe at multiple ends from here. Then we say that it's a secant projection. Azimuthal projection is trying to take care of those at the poles. If you look at the ones we've seen so far, those at the poles cannot really give us any good information because each and every time they do not have contact with the projection surface that we are using. So azimuthal projection has this flat surface that is just fixed on top to touch the poles. And once it touch the poles, we get the true shape of objects that are within this area. Places that are like Africa, if you look at this area, because Africa is not in contact with the azimuthal plane, we are not going to get the true shape of Africa. This is an exaggerated form of the size of Africa. And so this is also preserving areas and distances, but only in places that are in contact with it. And so we need to be able to know where is our data coming from, what projections do we need to give or to put it in before we can start to do our work. Okay, so we have looked at projected coordinate system. We have said that projected coordinate system is important because in projected coordinate system, we get to convert the coordinate degree, longitude, and latitudes that we have in geographic coordinate system onto a plane, which basically allows us to put the data on a flat plane like a paper or on our computer screen. And we can be able to measure and see how things are in the real world. Okay, so we've talked about geographic coordinate system as well, and we've spoken about how geographic coordinate systems are created and how they are developed. And we are going to put them together at the end of this class. But before then, I want us to talk about coordinate authority or coordinate system authority. You might see this in some of the softwares, especially in Esri. When you review the coordinate source of a data, you might see authority, and you can see something like Esri or sometimes EPSG. I'm going to explain what these things are, and then we would come to be able to understand what the profile of a coordinate system is, and we can explain every bit of the parameters. Now, somewhere in the, I think, 1880s, or yeah, there's a group called the European Petroleum Survey Group, and in short, it's called EPSG. And now it's called the Committee of International Association of Oil and Gas Producers, OGP. Now, this was just a consortium of companies that are involved in exploration and extraction of oil worldwide. And for the sake of their own members, they decided to compile they decided to compile coordinate systems that are being in use in various areas. And these coordinate systems they gave it um, an ID, basically using the WK WKID, which is like there's the full name is well known identifier. They gave it a WKID, or they use a WKT, which is the well known text. If you don't know about WKID or WKT, we can easily check them on the internet. But it's a protocol. It's more like a text protocol of documenting stuff. So they took this coordinate system and then they gave them an ID and they published the data in 1985. Now the geodetic parameter data set that was published by EPSG Group in 1985 for their members became popular because many people were using it. It became a public registry for geodetic datums, and it has information about the datum, the spatial reference system, the earth ellipsoid, the coordinate transformations, and the related units of measurement. Now, every year they try to update it. It is assumed that it is updated between 2 to 6 times in a year, depending on the number of new informations they receive. But they do now receive information from some government organizations and some geodetic groups in different countries. So depending on how the new ones they receive. We've already spoken about how geographic coordinate systems are created and how countries create their own due to the issue of finding the good fits between the spheroid and then the geoid, which we've already handled that in the previous class. If you don't understand the statement I just made, it means you have to go and watch the previous class again, which will still be on this YouTube channel. And this update that they've done, they have assigned the code between, I think now it has increased, but the code was between 1024 and then 32,767. And with this code, many open source GIS softwares are using this code. This code are just reference to a coordinate system. And so you might see code like EPSG maybe 4236 or 4326. That is like a reference code by EPSG parameter dataset that refers to the WGS 1984. So the GIS systems start to use the EPSG code as a unique identifier, that is a spatial reference identifier for coordinate reference systems and projections that enables different transformations and stuff. So you might see a lot of them. However, there are times where SG has also claimed that they get some data or some uh, coordinate systems which are not yet published by EPSG. And so SG also published their own and they also use the WKT or the WKID protocol to encode these coordinate system. And so when you see coordinate system authority, if it is EPSG, it means that data, that coordinate system is published in the EPSG. If it is SG, then it means that it was published by ESRI. Basically, that is what it is. But this is where the EPSG come from. This is how the EPSG was developed, and this is why you may see it in many open source software, because now it has become more like a standard and universal public registry that everyone refers to. It's online, it's available, you can always check them out or download them if you want. So now let me give you a practical example. So this is a print of, or this is a view of uh, a coordinate system review. I think this is coming from Esri documentation. And if you look at this is a projected coordinate system. It's a projected coordinate system because if you look at the details, it tells you that this is a projected coordinate system, and it has the WKID, which is the code. This is the code, and this is the authority. This WKID was done by Esri. Now we've also said from the beginning why we needed coordinate system in the first place was that we needed some sort of standardization. And so in a coordinate system, in a projected coordinate system, many of them are in meters. And so the linear unit is also recorded. So the moment you use a projected coordinate system, you are likely to have your every measurement or anything that you measure on the map is by default in meters. Unless you are using a national based coordinate system. Like we said that countries also develop their own coordinate system. So if you are using a national based coordinate system, mostly on the country level, they are more interested in details. So their linear measurement is in feet. So whenever you see a projected coordinate system that has a linear unit of feet, it means it's a country level coordinate system. We have false eastings, false northings, and options. These are parameters that are used in calculating the datum. So when you are calculating the datum, we need a reference to the equator, we need reference to false easting and false positive. Stuff. False northings and false eastings. However, we still have the geographic coordinate system here. And here it says that it's WGS 1984. If you see the well-known identifier or the WKID, you see that it's 4326 and the authority is coming from EPSG. The angular unit is in degree, which we've already spoken about. This is the prime meridian that was used. This is the datum that was used. This is the spheroid. I remember in our previous class I explained that mostly coordinate systems are named after the datum from which they were created. And the datums are mostly named after the spheroid that was used in doing the calculation. This is the semi-axis and the semi-major axis and semi-minor axis that was used to define the spheroid. We've already done this in the Geographic Coordinate System class, so I hope that helps. And this is the inverse flattening value. Now, interestingly, whenever you see projected coordinate system, you will see geographic coordinate system as well. This is because geographic coordinate system tells us where on Earth the data comes from, which we also spoke about in the previous class. And projected coordinate system tells us how do we draw this on the flat surface. And so we said we needed projected coordinate system in the first place because we need to bring the data on a plane because the data is coming from a curved surface. Now, the projected coordinate system does not necessarily give us the location of the data, but it converts the geographic coordinates or the geographic coordinates of the curved surface, which is already the position, into something that we can be able to work with in a planar surface. And this is a geographic coordinate system. This is a data coming from a geographic coordinate system. And you don't see any projected coordinate system here. What this means is that when you see a data when you review the coordinate system details of a data and you see only this, it should tell you that the data is not projected yet. If you see this, then it means that the data is projected. There are times you see this, but you will not see some informations will be missing, which we hope that you will be able to catch that one up during the practicals. But then this is basically what I want you to understand. When it comes to coordinate system, we have been able to talk about the fact that coordinate system helps us to identify where on earth the data comes from. Secondly, it provides a framework. It's a standardization and it provides a framework for us to ensure that works or data collected can be integrated. They can be put together. And so things like unit of measure, things like the values that we use for the values we use for estimating our the things on the map, yeah, are all in the same plane. So we do not want people don't just wake up and say, me, I would measure my stuff in feet. If you want to measure stuff in feet, you have to do the conversion. But the coordinate system provides a very good foundation for us. So this is one of the standardizations you would see in GIS. We are going to speak more about some concepts in our later classes where you would see that we have a lot of standards and we use what I term as a decentralized standard. So the standard is such that there is a general umbrella, however, there are some local details and some people deduce sub standards based on their needs. And so you have some standards at the local level, you have some standard at the national level, sometimes on the maybe subcontinental level and stuff. So I hope this class was informative. I hope it has helped you clear so many things that you see always on the in your GIS software, but you don't know what they mean. And like I said, coordinate system is one of the complex things that you can deal with. In understanding, in theory, understanding it, and even in practice, getting to understand or figure out problems that are coordinate system related. We hope to be able to help you gain the skills of troubleshooting coordinate system related problems. However, the best way to learn is to practice and get the practical exposure and experience. Read and practice multiple times. The more you do, the more you connect the dots intuitively. And so we hope that you'll be able to do this yourself. And we'll see you in the next class. Until then, goodbye.